No question on.
Okay. All right. So special functions, integral transforms, and transform methods. We use functions, integral equations. That's roughly going to be the content of the course. Again, it kind of depends on how much time we have. If I don't cover all of it, it's not a big deal. What I do cover, I want to make sure that you guys actually learn the problem. Okay. So feel free to ask questions as much as you want. If I don't get to finish all the material that I set out to, it's not a big deal as long as we learn some interesting things along the way. Okay, so I like to start each new section with a, let's say, a physical problem. Right? I want you to keep in mind this problem as we go along and anchor your intuition to that problem. So the problem I want to start off with is related to the following systems. So consider the form. I have a pendulum, vertical pendulum, some mass, some length, it makes some angle with vertical of theta. Okay. So the pendulum problem is an old problem, and it's an example of a harmonic oscillator type problem, which you will have encountered before. These types of oscillators are hella very important in just as general laboratories for extracting physics. So Newton's law for this pendulum problem tells me that the acceleration of the pendulum, the angular acceleration of the pendulum, right? So this is the second derivative of theta with respect to time. Is minus some constant times sine of theta, right? So you can work out the geometry of this problem, write down a free body diagram, you can work out the forces. I've captured all the mass and length information in this constant k. I don't really care what the constant is. The point is, in fact, I make it more obvious. The point is that it's a positive number. Okay. So at this point, you would write down this equation. This equation is essentially Newton's law. And not knowing how to solve this equation, because there's a sine theta there, you make an approximation. Okay, so the approximation that you would make is sine theta, sorry, theta is small. And if theta is small, then sine theta is approximately theta. So then you would say, oh, this is just approximately minus k squared times theta. And now I have simple harmonic motion. I have a function, I'm looking for a function of theta, whose second derivative is proportional to theta itself, except with the negative sign. Right? And then you think sines and cosines, great. So I can write down a solution. Okay, so this is the simple harmonic approximation. Question that I have, the question that I would like to leave you with, the question that we're going to get to in a little bit is very simple. What do we do if theta is not small? How do we solve this equation if theta is not small? So sine theta is not approximately theta, and I don't have simple harmonic. Okay. So that's the question that we'd like to answer. What happens when the pendulum problem, when I can't approximate the motion of the pendulum by simple harmonic motion? All right. So we're going to build our way to answering that question. But for the moment, I want to start off and just remind you about something that I hope you know already. This is the Euler gamma function. Okay. So the Euler gamma function is a generalization of the factorial function. Right, and the factorial function n factorial, you know, is n times n minus 1 times n minus 2 all the way through to e times 2 times 1. With the understanding that 0 factorial is defined to be 1. Because the equality sign will take to mean the definition. But the point here is that the factorial function is defined for integers. In fact, positive integers. Okay, it's not clear to me using this definition how I would go about defining the factorial of a negative number or a fraction or any irrational number. Right. So this is a bit of a drawback. So this is defined only when n is a positive integer or 0. Okay. In fact, let's say minus 7. Okay. So the Euler gamma function is a generalization of the factorial function to the case where n, let's call it x, is no longer just a positive integer. So, by way of definition, you would have seen something like gamma of x defined to be the integral from 0 to infinity of t to the x minus 1 e to the minus t dt. Okay. This is a defining equation for the Euler gamma function, and x here is now any real numbers. So in this way, and I'll show you explicitly, you can generalize the idea of a factorial to include any old real number that you want. Okay. And the way things work in mathematics, and especially in applied mathematics, theory of physics, is try to push your luck as far as you can. Let's do that. All right, so why start with real numbers? You can extend this definition with Z to be some complex number. So one question you can ask is, what complex number? Does it work for all complex numbers? The answer turns out to be yes, but there's a bit of a caveat that we have to explore. Initially, if I look at this, whenever I write down any integral representation, if I write down any integral expression, you should always ask yourself, when does the integral converge? Okay. So in this case, the integral converges when the real part of Z is positive. That's the condition, and you can test this in any which way you're comfortable. very happy to just leave. But the definition as I've written it down holds whenever the real part of Z is positive, and that's because that's where this integral converge. Okay. But like I said, we're going to try and push this as far as we possibly can. So then I'm going to need to extend this domain here from the currently holds for just the right half complex plane to the whole complex plane. But I'm going to need to tell you how to do it. So let's start then, and I want to explore some of the properties that follow, properties of gamma function that follow from this definition. Anyone who came in late, just write your name down. Pass it to the back as well, just so that I know who to add and who to subtract from the bullet. I don't know. Okay. So the first point to note is that even though I define this thing, this function, for positive real part of Z, I can always analytically continue it to negative real part of Z as well. So from the from the right half plane, I can analytically continue this to the left half plane as well. The problem is that I will get singularities of this function at various places. In fact, I'll get an infinite number of singularities at all negative integers. Okay. And these are not bad as singularities for those of you familiar with singularities in complex plane. They're just poles. So we can analytically continue. I'm going to do this a little bit fast because it's roughly a review of things that you should have known from theory of complex analysis of complex variables. And if you don't, it's in my notes, which I will upload later today, so you can take a look there as well. So we can analytically continue. Gamma of Z to the left half complex plane. Oh, sorry, that's the lower half plane, right? Left complex plane. But gamma of Z will have poles as singularities there. In fact, they will have one of them for each negative integer all the way through to infinity, minus infinity. And any complex value function that is analytic everywhere but a finite, but a countably infinite number of points, all the negative integers, where we have poles, it's called a meromorphic function. Okay, so the gamma of Z will be meromorphic. That means analytic plus by default. So let's see if we can try and unpack why the gamma function is the generalization of the factorial function. So one of the things about the factorial function is that this definition here follows from the fact that n factorial is n times n minus 1 factorial. So that's the property that we're trying to get to. Can I show that gamma of Z is z times gamma of z minus 1. Something like that. Okay. So to do that, I want to do the following. We're going to start off and take a derivative. And I'm going to take a derivative of t to the z times e to the minus t. And I'm just differentiating with respect to t, assuming that everything is perfectly fine with z. So if we treat z as a normal number, then that's z t to the z minus 1 e to the minus t minus t to the z e to the minus t by the product. So now I integrate both sides with respect to t. From 0 to 30. And you'll realize that all I've done is just a fancy way of saying integrate by parts. Okay. So I integrate from 0 to infinity of the derivative z t, the integral of the derivative is inside here. So I can evaluate 0 to infinity. And that's equal to the integral from 0 to infinity of z t to the z minus 1 e to the minus t minus the integral from 0 to infinity of t to the z e to the minus t dt. Okay, so this is nothing but integration by parts. Of which we're going to be doing a hell of a lot in this course. Okay. So on the left-hand side, I have basically this is just z e to the minus t between 0 t equals 0. Right? When t is infinite, the exponential dominates and kills it. When t is 0, 0 dominates and kills it. So overall, this is just 0. And that 0 is equal to things on the right hand side. This is an integral with respect to t, so I pull z out. And what's left is the integral from 0 to infinity of t to the z minus 1 e to the minus t dt. Which, what's just sitting above here is nothing but gamma of z minus the integral from 0 to infinity of t z minus t dt, which you would recognize as gamma of z plus 1. In other words, we've proven what we set out to prove, which is that the gamma function, from our definition of what the gamma function is, satisfies the relation that gamma of z plus 1 is z gamma. Okay, this is the recursion relation that you're familiar with from factorial functions. Any questions? Big question online. Okay. Moreover, part 3, gamma of 0, gamma of 1 is what I get if I substitute 1 there, 1 1 is 0, so that's just the integral from 0 to infinity e to the minus t dt. Just 1. In other words, gamma, when its argument is an integer, is nothing but n plus 1 factorial. This is for n equals 2, 3, 0. Okay. So what we have here, and I'm going to be using this terminology very frequently, is an integral representation for the gamma function, right? From which we can learn some of its properties by exploring the integral representation. Okay. And you see, I didn't actually need to do the integral here. This property was derived by relating these two integrals to this integral, which I could do because it's a total derivative. Okay. So I haven't done any integrals, per se, but the fundamental property, this recursion property of the gamma function, follows essentially from the integral representation. This is the power of integral representations. Okay. Sometimes I can do the integral. That's this is easy. Okay. But in general, I'm not going to be able to do the integral. And in general, I'm not going to have to do it. Okay. I want you to return to this statement here, and let's unpack it. I'll tell you what I mean by a meromorphic function, and exactly what type of meromorphic function it is, because I understand it's probably understandable that you spend too much time talking about analytic configuration if you've done a course in complex analysis. So let's go back to property 1. Okay. So, how do I analytically continue the gamma function to the domain where the real part of z is negative? Well, is I could choose some value of n, n being an integer. So to analytically continue gamma z, so to the region where the real part of z is 0, I'll start off and I'll choose some number n sufficiently large so choose n large enough so that z plus n lies in the positive, lies in the right of that. In other words, the real part of z plus n is positive. Okay, so I have some number z, and I know that its real part is negative, so it lies somewhere less of n. I pick some number, think of some number, and I make sure that it's large enough such that this point, whatever it is, lies in the right half. And I know that on the right half plane, the gamma function is perfectly well defined because the integral will converge. Okay. So then, using this recursion relation, which relates gamma of z plus 1 to z gamma of z multiple times, it follows that gamma of z, and what I'm doing here is I'm dividing the by whatever these coefficients are once I continually apply this recursion relation, right? Is related to gamma of z plus n. Remember, this guy is perfectly well defined by all of those coefficients that are sitting in front of it. What are those coefficients? They're nothing but z times z plus 1 all the way through to z plus n minus 1. Okay. What have I done? I've related the gamma function in some region where it's perfectly well defined to another region. Remember, the real part of z is less than 0. So this is a definition of what gamma of z is when the real part of z is negative. Okay, this is what we want. And I said that I was going to have a bunch of singularities. Where are those singularities coming from? Well, anywhere that the denominator goes to 0, I'm going to be divided by 0. Where does the denominator go to 0? Well, at z equals minus 1, z equals 0, at z equals minus 2, minus 3, all the way through to 1 minus n. Okay. So this function here is analytic everywhere except where the denominator vanishes. In other words, it's a meromorphic function. Because it has simple poles at each of those points. You would recall that a simple pole is a pole of order 1. So it's only 1 power of z and 1 power of z plus 1. Here's a quick calculation. Show that the residue of gamma of z let's say gamma of minus n is just minus 1 to the n over n factorial. Any questions? You guys comfortable with the pace? Should I pick it up? Drop it down? Sorry. Okay. All right. So what I think I will do in general is I'll go until I've exhausted all the walls. I really don't feel like seeing any walls. Okay. So I've got 2 more walls to go. We'll go on to that.
Do you mind if we leave now because we have a bunch of.
Yeah, no, not at all. It will be recorded. You will have access. Okay. So. Let's count this as property number 4. So property number 4, I want to relate the gamma function to something called the beta function. The beta function is the precursor of, in theoretical physics, you call the beta function the Veneziano magnitude or Veneziano formula. And it's really the kind of, it was the precursor to string. This is where it all kind of flowed from patterns that emerged in the mathematical functions. Then it turns out that it's not too difficult to actually understand these patterns by just studying the gamma function. So I'm going to use this as an example of more properties of the gamma function. In fact, these are just some of the two particularly useful identities that follow essentially from this. So these two properties go by the name of beta function and the inversion formula. Okay. They both start off from the same general place, so we might as well do that at the same time. So notice the following. If I take gamma of A and multiply it by gamma of B, where A and B are some generally complex numbers that satisfy the properties that we need for the gamma function to be defined by its integral representation, then the following is true. And all I'm doing is writing down the integral representation from 0 to infinity, t to the A minus 1, e to the minus t, dt, and integral from 0 to infinity, t to the b minus 1, e to the minus t, dt. And in fact, to keep things a little bit clean here, let's call this t tilde. It doesn't matter, it's a dummy variable in a definite integral, so I can call it whatever I want. But I want to distinguish these two because these are product of two single integrals, which, if you know how these things work, I'm going to try and combine into a double integral. Right, so then I need to keep track of what my integration variables are. So the one it's t, and the other one it's t tilde. So now let's set t equal to x squared and t tilde, sorry, equal to y squared and t tilde equal to x squared. Well then, when I convert from t to y squared, this product, gamma of A, and you should check the details here, becomes 4 times the integral from 0 to infinity of y to the 2b minus 1 times e to the minus y squared dy times the integral from 0 to infinity x to the 2a minus 1 e to the minus x squared dx. Right. So for those of you who are familiar with the terminology, perhaps statistical mechanics, perhaps statistics, these are moments of Gaussians. Right? E to the minus y squared is a Gaussian integral. Question?
It's just A did not be solved.
Yeah, it should.
So the X goes in P.
Yeah. It doesn't really matter because we're going to combine them. They combine in a symmetric way. So let's combine them. So these are two single integrals, like combine into a double integral. Going from 0 to infinity along y and 0 to infinity along x. So if you think about what we're doing, here's our xy plane. We're going from 0 to infinity along x, along y, along x, from 0 to infinity, and 0 to infinity along y. In other words, our double integral covers this domain, let's call it D. Okay, so I do the integral over d of e to the minus x squared plus y squared times x to the, in fact, you know what I'm going to do? Let's just leave this at b, this at a, change this. So it's x to the 2a minus 1, y to the 2b minus 1, dx, dy.
Those should be minus 2s, right?
So it should be minus 2. No, because I get one factor from the measure. So what we've done here is we've converted the iterated integral into a double integral. Okay, and the double integral is taken over the first quadrant, and now I can change variables again to make my life easier. Right? What I need to do here is do an integral over this first quadrant. Okay. What we're doing is a Cartesian integral of the first quadrant, so we're integrating with respect to x, with respect to y, but I could just as well integrate with respect to r from 0 up to infinity, and then sweep that line with respect to theta. So I can change variables again to polar coordinates by defining x as r cos theta and y as r sin theta. Then this integral gamma of a gamma of b is just 2 times the integral from 0 to infinity of e to the minus r squared times r squared to the a plus b minus 1 d of r squared. Again, it's a 1 here because the 2 multiplies these 2. Times the integral from 0 to pi by 2 of cos to the 2a minus 1 theta sine 2b minus 1 theta d theta. Yeah. I've changed, so this here is R, D, R. So you agree? So all I've done is I've rewritten this guy as a half D, R squared. Just because everything that occurs in this integral, in the integrand, occurs as R squared, or I can write it as R squared. So now I can just change variables. Okay. So now let's label this equation. So in equation 1, let's set t equal to sine squared theta. So if t is sine squared theta, dt is 2 sine theta cos theta d theta. And substituting that into here, gamma of A, gamma of B. Notice this guy here, sitting out here. Again, just r squared is one variable. Okay, so it's an integral from 0 to infinity of variable to the some power minus 1 e to the minus variable d variable. That variable happens to be r squared. Don't let that fool you. Exactly this. Where that variable is a plus b. In other words, this guy here is just gamma of a plus b. So this first b is here. If I take this factor of 2 and incorporate it in the measure for the integral, then the remaining bit, when t goes from 0 to, when theta goes from 0 to pi by 2, t goes from 0 to 1. Okay, so this is an integral from 0 to 1 of 1 minus t to the a minus 1 times t to the b minus 1 dt. Okay, again, all I'm doing here is I'm playing around with these integral representations, changing variables a couple of times, keeping track of the limits, and what I've managed to show is that gamma of a times gamma of b is proportional to gamma of a plus b, and the proportionality thing is this integral here. Okay, question, yes.
Two.
What's your name?
Dylan.
Yes. Oh.
Coefficient of 2.
Yep.
Should that?
I took it in to the Okay. Alright, so let's label this guy because we're going to use this now. And follow on question. If I set A to be 1 minus Z, now A and B I didn't tell you anything about, right? They can be whatever I want. As long as they satisfy the constraints that I need for the integral to converge, perfectly happy. Right? So now I'm going to make some choices. So I'm going to choose A equal to 1 minus Z and B equal to Z. So in this case, on the left-hand side, I have gamma of Z times gamma of 1 minus Z. Exactly. Right. That's question 1. Right, so we're going back here. On the left hand side, I have gamma of Z times gamma of Z 1 minus Z. On the right hand side, I get 2 times the integral from 0 to infinity of Z times 1 minus, Z plus 1 minus Z. Z's cancel off, so that's 1 minus 1, that's 0. So that takes this guy out. Right? So I just have e to the minus r squared d of r squared. Okay. That's just an exponential integral. Don't let the r squared fool you. We're not doing Gaussian integral, we're integrating with respect to z squared. On the other hand, the remaining integral from 0 to pi by 2 is just cot of 2z minus 1. Sorry, cot to the 2z minus 1 theta d theta. The exponential integral, as we've done before, is just 1. So this is just 2 times the integral from 0 to the power of 2 of cot 2z minus 1 theta d theta. This integral is an elementary integral, believe it or not, if I pretend that z is any old number. And you can do it just by substitution. If you define, let's say, w to be cot of theta, and you've got an integral of this thing here as little exercise. Show that the integral from 0 to pi by 2 of cot 2z minus 1 theta is equal to pi over 2 times cosec of pi z, whenever z is between 0 and 1. And if I substitute this result back into here, I find that m of z times m of 1 minus z is just pi cosec of pi z. And that relation, m of z times m of 1 minus z, is pi cosec of pi z, is called the inversion relation.
Yeah. Are these A and B is exchanged in that equation, in equation 1? Because if I put B as Z, so that's 2Z minus 1, so sign is on top. So it should have been a tan instead of cot.
Sorry.
So if I substitute B as Z, so the power of sign is 2Z minus 1. And cos will be minus 2Z plus 1. So cos will go in the denominator and we get a tan instead of a cot. But if we exchange those two, then we'll get a cos.
Oh, possibly. This is again symmetric. That's what you mean, right?
Yeah.
The left hand side is symmetric. Okay. All right, good. So let's stop here. Let me just give you a hint here for this. To do this integral, you need to do the integral over following contour. Say gamma, and this is minus 1. So if you use that contour on that complex plane, you can immediately verify this. Well, not immediately, but you can make one change of variables and then the contour. All right, so let's stop here. And I will pick it up on Friday and we'll talk about the beta function and its relation to the Veneziana, the two, and okay. Right.
Any questions online? Okay, I was having an issue with the network, so I was in and out. I will re-follow on the YouTube as well.
Okay.
Yeah.